Okay. Hello, everyone. Thanks for coming. I expected a few less people. I would have gone to the Kubernetes talk. So thank you for coming here and me talking about NATS. Today I'm going to talk about NATS. NATS is a messaging system hosted under the CNCF umbrella. Who doesn't know who CNCF is? CNCF is a foundation that tries to collect and promote a set of projects that make it easier to implement cloud-native applications. So it's just a place where you can go to look for projects that can help you implementing distributed system, basically. Sorry. Some quick words about me. I'm Federico. I work at List. It's a company based in Pisa, not far from here. It's a fintech company. We make software for interacting with the financial markets. So there are a lot of messaging, a lot of data that flows in every direction, and we have to handle. My Twitter handle is FedePaol. FedePaol is basically my handle for everything. If you wanted to comment after this talk and say that you didn't like or you liked it or whatever, you can ping me there. I'll try to reply. I'm just a user of NATS. I'm not affiliated in any way with the developers of the company behind the messaging system. Let's start with what is the reason for messaging. Messaging came in place because the way we build and develop and architect our application is moving and is moved from big monoliths to distributed systems and beyond, like serverless stuff. Together with the distribution of our services, several patterns of communication emerged. The most common one was having our services interact through REST. gRPC is another way, but there are some kind of problems that are better mapped using messaging and messaging-based patterns. For example, let's see, what are the good points of messaging? Using a messaging system decouples our endpoints, which means that a producer of a message doesn't have to know who is going to consume that message. A consumer of a message doesn't have to know where that message is coming from. They are decoupled. This helps us for scaling because since they are decoupled, we can throw in and throw out our systems new consumers and new producers without changing any kind of configurations. And it also enables other ways of communication between our services. For example, event sourcing, where consumers want to be notified and to be aligned of the state of a source. And this alignment is done through deltas sent out by messages. And also, it enables all the kinds of reactive paradigms which allows our system to evolve in response of an event. That response can trigger other events thrown inside our system, and that can be the way our system evolves. There are a lot of messaging systems. Each one has its features. Each one has its fallacies. So what do we need to look for in a messaging system? There are a lot of aspects. What are the messaging patterns that messaging systems support? Is it just pub/sub? Does it support request/reply, fan-in, fan-out, any kind? What are the patterns that a messaging system support? What is the durability of the messages? Will the message be there even if nobody consumes that? Will it have a timeout after which the message expires? What are the ordering guarantees? Will I be sure that even if the source emits the messages in a given order, the consumer will receive them in the same order the messages are produced. And also, what are the routing capabilities? Can I have a subscription to given subjects? Does the system support or not wildcards? And another thing which is important, what is the experience from the developer point of view? Do I need to make a voodoo ritual in order to interact to that system and to configure it and turn all the knobs of the system in order to have it behave like I want, or is it easy to deploy and to configure it? And other things like performance, authorization and authentication, and so on. So what makes a good communication system? I think there are two sides, two extremes of a communication systems. The farthest extreme is the enterprise service buses, which was quite popular during the service-oriented architectures era, where a lot of the business logic was kept in the bus itself. So the bus was doing a lot of stuff, even business logic stuff. So it was really hard to understand what our system were doing, because the logic was split between the endpoints and the bus itself. So the bus was doing filtering, mapping, transformations of our messages. So it seemed easy at first, but then it resulted in difficult to maintain architectures. The other side, the complete opposite end of that side is what Martin Fowler advocates in his article about microservices, where he says that the community, the microservices community, prefers another approach where the bus is as dumb as it can, smart, and all the smartness, all the business logic is held in the endpoints, which are the pieces we maintain and we develop. So what we can say about nuts, I think we can say that nuts is dumb the way Martin Fowler advocates, but not dumber. It's dumb enough, it does a few things, and it does them extremely well. So let's start seeing it before I will drink some water, because sorry. Okay, so let's start with the protocol. The protocol is text-based. It's just a handful of commands. We have pub to publish a message, sub to subscribe a message, to a given subject. Message is when our endpoints are notified of new message, and unsub. It's text-based. You can just telnet to a NATS server, send this command. The commands are, the messages are ended with carriage return plus line feed, and you'll see the server reply back. There are also other few messages that are used for handling the connection, like connect, info, and ping. Ping is particularly useful because not always the socket, the fact that we perceive the socket as connected means that the connection is really working. So there is a ping mechanism between the endpoints in order to understand if the connection is really working or not. NATS, the subjects are strings, are tokens separated by dots, and the NATS support wildcards. So you can subscribe to something that looks like foo.bar or foo.star, which means that you are looking to match to foo.something, but foo.star won't match something else. If you want to do that, you have to use the foo.greeted and sign. And also something that was kind of unexpected from my side is that you can put wildcards also in the middle. So how does the server look like? The server is a single Go executable. is very small. The memory footprint is very low, and all the servers of a cluster forms a full mesh, which means that each server is connected to each other server of the cluster. There is also a gossip-based auto-discovery, which means that if you want to add a new server to the cluster, you configure one or more servers as a seed server, you point the new servers to that seed server, and automatically all the nodes of the clusters and all the clients connected to the cluster will get notified of the new addition or if a server goes down. So again, it's easy to scale up and scale down the cluster. And also, as I said, the configuration is extremely easy. There is also a very small Docker image. You just run the server and you are done. As I said, it's a full mesh of servers, which means that two different clients are always at most one hop distant between each other. And when a client declares its interest in a given subject, the interest graph is propagated through all the mesh. So it will work. I mean, when a client connected to a node publishes a message, that message, given the interest graph, will receive any client interested in that message. What are the guarantees of NATS? NATS, it's at most once, it guarantees at most once delivery. What does this mean? It means that if a client is connected and is interested to a given subject and a message is published, it will receive that message. Otherwise, that message will be lost, will be thrown away. It's kind of the tree falling in the forest where nobody is able to listen to it. And also ordering. Messages are ordered per publisher. So it's, I think it's an important feature. The maintainer used to say that NATS acts as an always up dial tone. The emphasis is on the availability on the server. NATS was built with two things in mind: availability and performance. How does it do that? The NATS server behaves in a very selfish way. If the server detects a client as a slow client, which means that a given client is not able to keep up with the number of messages the server is sent into it, that client is marked as a slow client, and the server cuts the connection. A very few state is kept on the server, and this allows NATS to be fast and reliable. It doesn't have to do the extra work of trying to help the clients. It just cuts them away if they are not able to consume all the traffic the server is sent into it. So, what can we do with NATS? What are the messaging patterns that it supports? Well, of course, it supports publish, subscribe. We saw the messages. It's the core of how NATS work. The publisher does not assume the audience, which means that a client connected that publishes a message doesn't know and doesn't care if that message will receive 1, 1,000 of any subscriber. There is also a queuing mechanism. Queuing is, I think, a bit of a misleading term, because queuing means that a lot of subscribers to a given subject can form a group, and if that happens, only one subscriber of that group randomly will get notified of the published message. So you can use that for load balancing. If you want to have 10 consumers of a message load balanced between them, you just add them inside a queue group. The message will receive just one consumer. And you can, again, scale up and scale down just by adding new consumers. NATS also supports request reply. Again, we didn't see request reply messages in the message supported by the protocol. How does request reply work? Request reply is just syntactic sugar. It's built on top of the pub/sub mechanism. A requester, when sending out a request, also sends out a reply subject where it is listening for the reply. And this can also be used together with the queuing if you want to have just one reply of a given group reply to a given message. How do we use nuts with Go? First of all, let me say there are a lot. The protocol is so simple that it's really easy to implement a new client that interacts with nuts. There are a lot of languages supported. Some of them are officially supported by the maintainers of nuts. Some others are community-based. There are clients for any kind of language you can think of, the fancy ones like Rust or Elixir, or for some, God forbid, reason you want to interact with that with PHP or Perl, they got your back covered, and there are clients also for Perl. I don't know if anybody wants to use it anymore, but the Go client. The Go client is the reference one, the one that the other client should take inspiration from, and it does a bit more than just implementing the protocol. The Go client handles the reconnection to the mesh for us. It knows, it gets notified by those info messages of all the variations of the cluster. If it detects a disconnection, reconnects to the cluster for us in a very transparent way. And also, it buffers messages that are being sent out. Sending is synchronous. And also, it buffers them while a reconnection is happening. So, if your application wants to send out a message, the client detects a disconnection, you won't notice anything. The Go client will reconnect to another node of the cluster, and then will send out those messages up to 8 meg, but like everything else can be configured. And also, we said that the Go client, the NATS server disconnects a slow client, but the Go client keeps a buffer of the received messages in order to help your application to consume them instead of getting cut immediately. Let's see a bit of code. As I said, the developer experience is important, and it's really easy to interact with a NAT server. It's just a few commands. You just connect to the server, you publish a message, you publish to a given subject. The given subject is a string, and the payload is a slice of bytes. So the protocol is payload agnostic. You can put whatever you want there. You can put JSON or whatever. The subscription is easy as well. You just pass a callback to it, and also there is a channel-based variant if you want to get notified inside the channel of the incoming messages. Request reply. It's easy as well. You just send the message. Okay, sorry, I was forgetting. Request is the only blocking call, which is why we don't have a reply callback, but a response message. Request comes with a timeout you can pass in. Roberto yesterday said that it is important for us to block to have a way to block our long-running calls. So there is also a context-based variant where you can pass a given context in order to block the call after a timeout, and that context can come from some other way, some other place. So it can be propagated from another call or what. Replying is easy as well. You can pass a subject, the reply topic where you'll have to send the reply, and the message that you are receiving. So it's just a few lines of code in order to interact with the NAT server. Other things about the Go client. If you are interested in getting notified of the evolution of the connection, and you don't want it to reconnect transparently, you can implement callbacks to get notified. For example, if you don't want to send messages if the client is not connected. For some APIs, there are sync and async variants. There are also type-safe encoders. So if instead of having payload agnostic callbacks, you want to pass, there are, I think, two of them. There is a JSON encoder and also a protobuf, if I remember correctly. And as I said before, there are context-based requests to let the request expire. NATS is simple. It's very simple. It's a very low-level messaging system. But it's the same simplicity we like it and we learn to appreciate in Go. It's the same simplicity we build powerful things on top of. There are, and it is what kind of I appreciate in Go and I appreciate in NATS. There are no hidden costs. You know what you are getting. And it is a base where you can build something on top of. It's, let's see an example of what we can build on top of NATS. Let's say we have a source that is emitting the variation of a given temperature. Is an example. It can be data from a stock market, but again, the variation use a sequence number, so the source is emitting 0.1, nobody's connected, so those messages will be lost forever. Then a client comes and it wants to get notified of the state of the server. It will have to do two things in two different ways. It will have to request the current state, and also it will have to subscribe to the variations of the state. In this way, whenever time the client connects, it will get notified of the current state and also of the variations of the state. Otherwise, the subscriber would have to wait for the next update that would take a lot to happen or not happen at all. So the source will reply to that request with the current state and will keep what it's doing. So it will keep publishing the variation of the state. And this is a place where that smartness we talked about earlier needs to come in place. The endpoint must be smart enough in order to understand if it's, because the messaging are coming from two flows, the client has to be smart enough to discard any old message or any duplicate message. So it has to implement some kind of idempotency on its side, and also to understand if the message received from the reply is older than a fresher update, for example. This is just an example, but it shows that you can use NATS to build your stuff on top of. Performance. I think it's really fast. NATS comes with a lot of tools. There is a benchmarking tool On a laptop of mine, it achieved, so a machine like this, it was like 8 million messages per second with one publisher and 5 subscribers with 16 bytes big messages. The latency is quite low as well. There is a blog post series by Tyler Threat, who was a contributor of NUTS, so this can be a bit biased, but in his blog he compares a lot of messaging systems. If you are interested in how they compare and how they behave, it's something I would recommend you to read. There are a lot of posts where it compares Kafka, Rabbit, Redis, and NUTS. Other features of NUTS I didn't talk about. NUTS supports TLS out of the box. NUTS exposes some endpoints in order to monitor and to understand what's going on, how many slow clients are detected. They are HTTP based. You just get from them. It throws you a JSON with all the indicators. It supports an authorization scheme, so you can tell NUTS who is able to publish what or who is able to subscribe what. It's also token based, so you can say that Federico or that given authorization token, it supports both user and password or authorization token. You can say that Federico is able to publish to the foo subject but not to the bar subject. The configuration is currently file-based. You have to, the configuration can be reloaded, but you have to change the file somehow and send a SIG-HAP to the server. In the works, there is a way to demand, to delegate this kind of authentication to some kind of a webhook, but this is the current state. It supports authentication, as I said before, username and password, or token-based. There is a Kubernetes operator and a Prometheus exporter if you want those metrics and those indicators exported in a Prometheus instance. And this is the part where NUTS tries to be a good citizen of the CNCF because all the CNCF promotes the integration between the projects. As we said, NUTS is something you can build on top of, and it's what the developer of NUTS did. NUTS streaming is a complementary project of NUTS. If I should describe it in a few words, it's Kafka, but with no Java. So that would make us quite happy. The code name is Stan. Stan is the complete opposite of NUTS because the guarantee that NUTS streaming has to offer are the opposite of what NUTS offer, which is at least once guarantee. NUTS streaming acts as a log of messages. If the client is not consuming them, those messages will be there until they are archived. And if the client comes back afterwards, it will receive those messages. So if you are familiar of what Kafka does, it's basically kind of the same. What are the features? First of all, I should say that NUTS streaming uses NUTS as a bus. So it just takes advantage of NUTS to share the messages. But if you publish a message to a subject inside NUTS streaming, you won't be able to see that message if you subscribe as a regular NUTS client. And also you have to tell to NUTS streaming where NUTS, a flat NUTS instance is, or there is a version of the NUTS streaming server that embeds a NUTS server inside itself. Messages are encoded, as I said, it's a complete different protocol from NUTS that uses NUTS as a bus. It offers durable subscriptions, so which is, I think, something that is different from Kafka. You can give a name to a given subscription that your client is using. If the client goes away and will come back afterwards, the server will understand that that client was left behind, and it will send the messages to that client. So the client won't have to remember where it left. There are queue groups the same way I described for NATS. So the clients can form a group, and only one member of the group will get notified of the given message. It offers message reply. You can tell NATS server, give me all the messages from 1 hour ago, or from 10 messages ago, or from sequence number 23. Other features, you have to have a persistence. The persistence can be configured by using SQL or file or memory. Memory won't be persistent at all, but if you want to experiment with it, you can do it. Partitioning, you can tell some nodes of the cluster which channels, which subjects are assigned to it. It also supports clustering, which means that Raft protocol is used to guarantee high availability between the nodes of the clusters, and it also supports active-passive configuration. So it's another way to guarantee high availability because you will have to maintain the persistence in some way, for example, with the replication, and you can have active instances and passive instances. And given that the way the messages are stored, this is not a feature but an aspect of NAT streaming, it doesn't support wildcarding. I would have finished this talk, but when I was preparing it, I met something else, which is LiftBridge. LiftBridge is built by the same that Tyler Threat guy I was speaking before about the blog post series. And if you are interested in this kind of systems, it's definitely something I would keep an eye on because it's promising some features that are missing from NAT streaming, like wildcarding and log compaction, for example. And differently from NAT streaming, it can work together. So you can register to a NAT subject and see that the lift-read messages pass through. So yes, the take-home lesson from here is that I just hope I triggered your curiosity. I put another tool on your belt. The setup is really simple. It's really easy to write some lines of code to interact with the NAT server. Go home, give it a try, and it won't fit any kind of problem, but it fits some problems extremely well. And that's it.
Are there any questions?
Hi, thank you for the talk. Especially interesting because we're using Kafka at our company. Just one question. Does this persistent subscription work together with the queue groups?
Yeah.
Okay, cool.
You can have queue groups, and if a member of the group consumes a message, the next message will be sent to another member of the queue group.
Okay, cool.
I think it's the way Kafka works.
Yeah.
I think if you have to compare them, Kafka has a big, more mature ecosystem. It has a lot more features than NAT streaming. But if you want just to use the log thing, you can give NAT streaming a try.
Thank you.
You're welcome.
Hey, nice talk. Could you elaborate a bit about how the slow clients are handled by the NAT server?
Yeah. what I understood is that if the server is not able to send the data through the socket after a given timeout, the client is marked as slow and is disconnected. And also the server keeps a counter of the slow client clients that are notified inside those monitoring endpoints I spoke about before.
So quick follow-up. So it is immediately disconnected after timeout is.
Yeah.
Okay. Thank you.
It's the way it works. It's the way it allows the NAT server to keep as few state as it can, and so it's part of the reliability of the NAT server.
Thank you.
Hello. Hi.
Hi.
I've got actually two questions. Okay. One is about TLS.
Sorry?
TLS encryption. First part is the benchmark you did were with TLS or without?
Without. Yeah, you can benchmark if you download the benchmarking tool. You can pass it a parameter in order to benchmark with TLS. And also, I think they have a page, I don't remember where all the benchmarks are updated after new releases.
Okay, thank you. And the other one is in case of clustering cascading, the TLS is guaranteed end-to-end or just?
Yeah, you have to. I think you have to configure both the TLS between the endpoints and the servers, and also between the servers, and also for the endpoints themselves. It's 3 configurations, so you have to put in place.
Okay. And the other thing, you said that when a client disconnects and then reconnects,
yeah,
the nomadic client, the server will remember which messages were sent to the client.
That's for the NAT streaming part.
Okay, so okay. Thank you.
And also that happens if you use a durable subscription. So it's a parameter you pass to the subscription call, where you say that that subscription calls foo. Then if the client comes back again and says, I'm foo, the server will remember that foo was at message number 28 and will send message number 29. If you don't, it will send just the new messages, or I don't remember, there are quite a few parameters in order to tell the server from where the client left. It can be from a given place in time or from a given sequence number.
Hi.
Hi.
My question is, what's the scalability comparing to Kafka? So as far as I understand, NATs use the mesh, and if something happens, and how the consensus work, and how, like which level is which will reach a bottleneck?
I think it depends, meaning that flat NATs is more lightweight than Kafka, so it have to do less work. It's up to your application if your application want to remember a given state to ask for the replay of that state. So the work NATs has to do is less, and that's the reason why I think it's faster than Kafka. From a scalability perspective, you can add quite a few servers. It depends on the kind of interaction, because it's a full mesh. So you can't have, I think, I didn't try because the scale of application I work on is lower. But I think that if you have 1,000 servers, it will result in a lot of chattiness between themselves, because the interest graph needs to be propagated to all the nodes of the servers. So yeah, I don't have, an exact reply to your question.
Thank you, Federico.